Uh, this is a final review, and we will start with kinematics, move to dynamics, and then uniform circular motion and work in energy. We will not do too much on the mechanical waves because it is recently done and it is not as much as part of the physics 20. Okay, the very first thing that we need to clarify in the kinematics is the concept of vectors and scalars. So when we are talking about a vector quantity, what we are asking for in order to fully describe that is to define what is the magnitude and what is the direction of this quantity. So you cannot identify a vector quantity if you are stating only one of them. You have to state both the magnitude and the direction in order to fully describe vector quantity. In a difference with a scalar quantity, in order to fully describe it, you just need to identify what is the magnitude. And of course, when we are saying the magnitude for both of them, the vector and the scalar quantity, it is great to identify the units as well, because the units will give you the hint of what quantity you are dealing with. It's a speed, is a force, is a displacement, or so on. Now, when we are classifying, or the quantities that we will use in mostly in physics in terms of vectors and scalars, are quantities as displacement. And displacement is known with letter D. And every time that we are dealing with a vector quantity, we have that little arrow on top. And the units, international system unit for displacement, are in meters. Next, a vector quantity that we will deal a lot in physics 20 is a velocity. And velocity is with letter V and this little arrow on top, and the units for it are meters per second. Another one is acceleration. And the unit, or the letter that we assign acceleration, is A, and the units for it are meters per second squared. And then on top of this, what we do is force when we move to dynamics. And the force is usually with letter F and with a subscript that identify what type of force you are dealing with. And the units for force are newtons, or we can say kilograms meters per second squared. So both of them are the same, even though the newtons have taken the attributes on the international system units to honor the work that Newton have done in physics in general. Scalar quantity is corresponding scalar quantity of the displacement is distance, and we assign it with letter D, and the units for it again are meters. For velocity is speed, and again we assign it with letter V, and the units are meters per second. Acceleration doesn't have a corresponding scalar quantity. However, another scalar quantity that we will use a lot is time with the letter T, and the international system unit for time is in seconds. And then we will work a lot the energy, and this is the biggest misconception. Any type of energy or work done in an object or by an object. And the international system units are newtons times meters, or very often we say joules. Now, the energy, when I say energy, any type of energy that you are dealing with. Another quantity that we will work a bit on physics 20, that is a vector quantity, is that is known as the field strength. And the one that we will see, or we have seen, is the gravitational field strength, which is lowercase g. And we will talk on this when we deal with this in physics 20 and mostly on physics 30. Okay, since we know how to work with a scalar quantity, because what do we do in a scalar quantity? We say it's positive or negative, or we just simply add them with either the signs or not, depending on the situation. The problem stands or appears now to how can we work with a vector quantity. So when we have a vector, how can we operate with a vector quantity? Before we move to how to operate with a vector quantity, we have to clarify how can we identify a vector quantity. And there are three ways that we identify it. The first one is using, and this is the one that is used mostly on physics, northeast, south, west axis. Next one is using bearing, which is with the north axis, in the relation to the north axis. And the third one is with positive x-axis. So this one here, positive x-axis. We have seen that bearing and positive x-axis is barely used in physics. So for the purposes of this review, I will focus more on northeast, southwest axis. If you want to know about bearing, you can refer to the videos that are on the lessons. So now, when we are identifying a vector, let's say a vector A with magnitude of 15 meters per second at 20 degrees north of east, what we are stating here is we are stating the magnitude. So this is the part that deals with magnitude, and always we add the units there so that we know what is the quantity that we are dealing with. And this second part here, describing a vector, is dealing with direction. So what the magnitude represents is the length of the line segment that graphically represents the vector. So the length of the line segment, if we have a vector that is, this is vector A, then the length of line segment here represent the magnitude of the object, of the, not the object, of the vector, magnitude of the vector. And then the direction is telling us where is the vector standing in the relation to the northeast southwest axis. So as you see here, the direction has two parts, has the angles and the northeast southwest direction or ways that we represent. So now the way that we read a vector is by starting as, or the way that we represent a vector in the northeast southwest axis is by looking at the angle. So we have northeast southwest axis. On this case, what we have is between north and east. So it is somewhere on this part here, the vector that we are dealing with. And then the first letter here is asking the question, where is the vector going? And the second question, or the second letter, is saying starting from which point? So you will see here that it is starting from east, going north at 20-degree angle. So the way that you will represent this vector is a vector A, that the line segment of this vector will represent 15 meters per second. And it is starting from east and it is going north at 20 degrees. One way to look at this, if you don't remember the questions that you have to ask, is you have to see like it's the north of east. So when you are standing at east, you see that you can head south or you can head north. So now this is saying to you that you are going the north of east. Okay, sometimes this is confusing to the students, and it is important to solidify this knowledge any way that makes sense to you. It doesn't really matter what is the way. Is this one, or you are saying, oh, I'm standing at east here, and I'm going the north of east at 20 degrees. Now, why is important to know how to represent graphically a vector? Because what we do is we find the horizontal and vertical component of the vector. Why do we do this? Because we need to operate with vectors, and the way that we operate with vectors is by finding the horizontal and vertical component of the vector. So if we have a vector, any vector, let's say that we have a vector that is vector A, that is 20 meters at 30 degrees west of north. So now the way that we find the horizontal and the vertical component is by the tip of the vector, this one here, we create a right angle triangle that includes the given angle. So you have two options to create a right angle triangle. One of the to go to the north axis, and the one that you go to the west, in this case, axis. Now, I say that create a right angle triangle that includes the given angle because it is easier and you don't do extra calculations. So the right angle triangle will be this one here. On this way, what do you have is a horizontal component of this vector, that is this one here, is another vector, and the vertical component of this vector, that is this one here. So this is the vertical component. And now using sine ratio and cosine ratio, we will solve for horizontal and vertical component. Horizontal and vertical component. But we have to keep in mind that the sign plays a huge role. So whatever is on the going up or going to the right is considered to be positive, and whatever is going down south or going west is considered to be negative. So in this case, what do we see is that the vertical component is positive because it's going up, and the horizontal component is negative because it's going to the west direction. This is how we find the components. But the other question is, how can we operate with vectors? The easiest one to operate with vectors, especially now after we have done so many adding vectors, is using components. So let's see how can we use components when we operate with vectors. Let's suppose that we have a vector A that is 50 meters at 25 degrees north of west, and a vector B that is 60 meters at 42 degrees south of east. So let's draw those vectors initially. We have a vector A that is between the north and west, and the magnitude of this vector is 50, which means that the line segment that represents this vector is 50, and then the angle with the west axis is 25 degrees. And then the other one, vector B, is between south and east, so east and south, and it is a vector that goes like this. This is vector B with magnitude of 60 meters, and the angle with east is 42 degrees. Let's complete the right angle triangle that includes the given angle. And then the horizontal component of vector A will be negative. The vertical component of vector A will be positive. And in this case, the horizontal component of vector B will be positive. And the vertical component of vector B will be negative. Now, what we are looking for is a resultant vector, and when we are saying a resultant vector is a vector that replaces the effect that those vectors have. So if we have A plus B, then replaces the effect that the vector A and the vector B has. And if we have A minus B, then it's the effect of that vector A and opposite of vector B has on the object. On this case, what I will do is I will do A minus 2B. So on this case, let's create the table right away. So we will have the horizontal component, vertical component, and here we will have vector A, and then we will have vector negative 2B, and at the end, we will have the resultant. So for vector A, the horizontal component of it will be negative. And in your calculator, please make sure that the mode of your calculator is on degrees times cosine 25. 50 times cosine 25 is negative 45.3. And for the vertical component will be sine, so it will be positive 21.1 meters. And for vector B, We have vector B here, but actually the question is asking us for -2. So -2, and then you open brackets, whatever is the horizontal component, which will be 60 times cosine 42, and it is positive 44.6, let's say. And for the vertical component will be negative and is related to the sine, and will be -2, that the formula, the relationship tells you to do, times -40.1. And now the resultant horizontal and vertical component of the resultant will be as a result of horizontal component of all of them and the vertical component of all of them. So -44.3 minus 2 times positive 44.6 is equal to -134.6, and the vertical component will be 21.1 minus 2 times -40.1, and this will be positive 101.3. Now, what those two numbers are telling us is saying that the horizontal component of the resultant is negative. So is this one here, -134.6, and the vertical component is positive, so it is 101.3, which tells us that the resultant is this one here. So now, in order to identify the magnitude of the resultant, which you can write it on this form or simply R, is using a squared plus b squared is equal to c squared, is 134.6 to the power of 2 plus 101.3 to the power of 2. And when we 134.6 to the power of 2 plus 101.3 to the power of 2, the whole thing square root will be 168.5 meters. And now we can identify the angle alpha as the inverse tangent of 101.3 over 134.6. Notice here that I ignore the sign because I know now where the vector is lying at. So I don't need to use the sign of the vector or the sign of the components because I know that the vector is in between north and west. And this will be 36.97 degrees, or we can say easily 37 degrees. And then we write an expression saying that it is 100, the resultant vector, 168.5 meters at 37 degrees, and this will be north of west. One more thing that is in the relation to vectors is how to operate them graphically. So graphical approach of vector operation. What do we have to keep in mind? That there are two ways that we add vectors graphically, that is known as the closed polygon method. And this is used when we have more than two. It's very well used, but you can use it even with two. And the other one is known as the parallelogram method. The closed polygon one deals with plotting vectors one after the other. So if you go vector A, vector B, vector C, vector D, and then the resultant will close the polygon. So we'll start at the starting point and we'll end at the end point. So this will be A plus B plus C plus D. And with the parallelogram method, everything starts at the same point. So vector A and vector B. So this is the starting point. And then you build the parallelogram, which is a 2D shape that sides are 2 by 2 equal and parallel to each other. And even the resultant starts at the same point. And this will be A plus B. When we have to subtract a vector, then what we do is, so if we have vector A minus vector B, and let's suppose that this is vector A and this is vector B, what we do is we start at a point and then we bring vector A first. So this is vector A. And then if we are doing the closed polygon method, then at where vector A is ending up, we will plot the negative vector B, which is the same as saying opposite of vector B. So if vector B is going this way, the opposite of vector B will be going in this way. So this will be negative B. And then the resultant will be A minus B. And if we have, let's suppose that we have for the same vectors A and B, we have to find the resultant as 2A minus 1 over 4B. Then what we do is at the point we bring double vector A. So for one vector A is this one here, and then another vector A is this one here. So this will give us 2A. And then if we were going with B, we will go in this direction because B is in this direction. Since we are going with the opposite B, then we will go in the opposite direction. So we'll go in this direction. But if this is vector B and we are looking for 1 over 4, negative 1 over 4 B, what we will do is we will divide it into 4. So 1 over 4B will be this one here. This will be negative 1 over 4B. And then the resultant vector will be this one here. 2A minus 1 over 4B. The second thing that we will discuss here is that is known as the graphs of motion. And when we are talking about graphs, first of all, why are graphs important? Because they give us a comprehension of what is going on in the motion of an object. We see it right away. We visualize the motion. And second is that we do calculations based on graphs. The three graphs that we discuss and talk on physics are the displacement time graph, the velocity time graph, and the acceleration time graph. The way that we deal with them is that when we know what is happening and what is the graph, the displacement or position time graph, and we want to calculate or figure out what is happening with a velocity time graph, what do? We calculate the slope. And if we know what is happening and what the graph, velocity time graph is, and we need to calculate and figure out what is happening with the acceleration time graph, again, we calculate the slope of the velocity time graph of parts of the motion or the whole motion of the velocity time graph. And if we know what is happening with the acceleration time graph, and we need to calculate and figure out what is happening with the velocity time graph, then we calculate the area under the graph, which can be positive or negative. The same thing we do when we are calculating the displacement time graph or the position time graph based on the information that we have from the velocity time graph. And again, the area under the graph can be positive and negative. If it is positive, then either the velocity is positive or the displacement is positive. And if it is negative, then either the velocity is negative or the displacement is negative. Okay, now we know that in what we have in motion are the two most, let's say, when we classify the motion, two are the type of motions that we see the most, is the uniform motion and non-uniform motion. So now, how will those two types of motion look on displacement time graph, velocity time graph, and acceleration time graph? Let's start with the uniform motion. So if we have a uniform motion, then the displacement time graph will be something like this, either going up or going down. Displacement time graph going down, or even negative. Displacement time, something like this. Okay, and then the velocity time graph, since what we are doing is we are calculating the slope, the velocity time graph will be corresponding of this will be a positive value because the slope of this graph is positive, or corresponding of this one here will be a negative value because the slope of this line is negative, and corresponding of this will be a negative value as well. Okay. Now the question may be, what is happening if the object is at rest? If the object is at rest, is not moving, so the displacement doesn't change, the velocity is equal to 0. Now, when we discuss and talk about the acceleration, on all the cases, the acceleration time graph in all those three cases is 0. Because this is a definition of the uniform circular motion, uniform motion. The uniform motion doesn't have acceleration. The acceleration is equal to 0. Now, we know now that the way that why do we calculate the slope is because the slope is the rate of change. So the velocity is the rate of change of the displacement. Therefore, we calculate the slope of the graph, displacement time graph. And when we calculate the slope of a horizontal line, the slope in this case is equal to 0. slope is equal to 0. So this is even mathematically proving that the velocity is the rate of change of displacement, and graphically is proving that too. When we are dealing with non-uniform motion, what we have is that we have an acceleration. So acceleration is not equal to 0, which means that the velocity is changing, is not constant, is changing. And the acceleration can be positive or can be negative. I will start with the velocity time graph, and then from there I will construct or show the displacement time graph. So when we have a non-uniform motion, what you may see in the velocity time graph is a graph that goes like this or like this, positive or negative. Guys, so that is telling us that the acceleration time graph will be positive for the first part of the motion and negative for the second one, for the second part of the motion, this one here. So we have established that what is happening at this moment of time, it's not the subject of physics. However, when we are finding the displacement time graph, then what we do is we have to consider the area under the graph. So now, just to make sense of what we are saying, I will put some numbers here, 5, 10 seconds, and this is 12 seconds, and then it goes to positive 15 and negative 12 meters per second. So area 1, area 2, and area 3. When we are saying area 1 will be this one here, area 2 will be this one here, this triangle here, and area 3 will be this negative one here. So area 1, since it is a triangle, will be 1/2 base times height, and base is 5 times height is positive 15. So 5 times 15 divided by 2 is 37, positive 37.5 meters. Area 2, again, is a triangle, so will be base times height, and 1/2 times 5 again, times positive 15, and will be positive 37.5 meters. And area 3 is a triangle again, 1/2 base times height, but now 1/2 times 2 is the base, and height will be negative 12, so will be negative 12 meters. Now, the way that we plot this information into displacement time graph, we'll start from 0. This is the assumption that we do. So at 5 seconds, because this is where the first part of the motion is ending, at 5 seconds, the displacement is positive 37.5. So positive 37.5 is somewhere in here. And this is the point that the object will be at 5 seconds. Now the question is, how is it going there? Is it going curve up, curve down, or straight? And since the slope of the velocity time graph is positive, then we'll go curve up like this. From 5 to 10 seconds, the object is moving 37.5 meters, which means that From this point, it's going positive 37.5, and positive 37.5 plus positive 37.5 is positive 75, positive 75 meters. So at the 10th second, the object is at this point here. But how is it going at that point? Is it going straight, curve up, curve down? Then what do is you look at the slope of the graph. The slope of the velocity time graph is negative, which means that the object is going curve down. Something like this. Okay, and then for 10 to 12 seconds, the object is moving negative 12 meters. So that means that from the position that is at positive 75, it's going negative 12 meters, which means that it will end up at positive 63 meters. So at 12 seconds, the object will end up at this point. And the question will be, how is it going at that point? Is it going straight or curve up or curve down? And since the slope of the velocity time graph for this part of the motion is negative, will be curve down. Now from this, we can calculate the total displacement as area 1 plus area 2 plus area 3 with the signs. So will be positive 37.5 plus positive 37.5 plus negative 12. And the total displacement will be equal to positive 63 meters. Versus total distance will be adding the areas without the sign. So 37.5 plus 37.5 plus 12, and this will be 75 plus 12 equals to 87 meters. So total distance is calculated as adding them without considering the sign, and total displacement you consider the sign. Okay, next subtopic for this review will be kinematics equation, which are generated from graphing, graphs of motion, kinematics equation. You have those kinematics equations in your formula sheet, but what do you have, like what am I referring to are those equations. So acceleration is delta V over delta T, and then we have V is equal to delta D over delta T. Next one is, so this is 1, let's say 2, and then you have displacement is equal to V initial T plus 1 over 2 A T squared. This is equation 3. Another one that you have is V final T minus 1 over 2 A T squared. This is equation 4. And then you have displacement is V1 plus V initial plus V final over 2 times time. And then this is, let's say, equation 5. And then next one is V final squared is equal to V initial squared plus 2AD. Now, the way that we approach those equations is that we sort what is given, see what they are asking. So given, asking, and then we see what is the formula that relates all of them. Keep in mind that acceleration can be positive and negative. So if it is accelerating, meaning if the final velocity is greater than initial velocity, then acceleration is positive. And the final velocity is less than initial velocity, then acceleration is negative. And plot in the values that you have and solve. Very often what you will see, especially when you are using equation 3 and 4, is that V initial is equal to 0, or if you are using 4, V final is equal to 0. How will you know this? The object will say starting from, or the question will say starting from rest or going to stop. Now this way, the equations that I use the most are equation 3 and equation 4, and then the rest are pretty much that you can generate everything that you need to know from those equations, along with the acceleration and the velocity. Okay, so now we'll take a look at the relative motion. Relative motion is a combination of two independent uniform motion. Two independent uniform motion. Typical questions, or what do we do in this case, is that we treat them as two independent uniform motions, and then we add the vectors of either the velocity, most of the cases, or displacement on other cases, on specific cases. Very typical question on the relative motion is the river question. So when you have a river that is flowing with a current of 10 meters per second going east, then you have an opportunity to go this way, straight as a swimmer, to go along the river, velocity of the current and the velocity of the swimmer, or to go against the river. So this is the river, and then you have the velocity of the current this way and the velocity of the swimmer this way. And the fourth option is when you are heading at a certain direction to end up across the river. So now what I will do for this is I will put some numbers and then complete all those cases. So let's suppose that we have a river, and then we have the velocity of the current is 10 meters per second, and the velocity or the speed of the swimmer in still water is 25 meters per second. So case A is moving with the current. Case B is against the current. C is across. And D is ending up across. Across. And for simplicity, we are saying that the width of the river is 150 meters. So on the first case, when they are moving with the current, then the vector diagram will look something like this. This is the velocity of the current. This is the velocity of the swimmer. So the resultant velocity will be this vector here. The velocity that the observer sees, the observer being here at the shore of the river, the observer sees is this one here. Always we start the solving it using the fact that the resultant velocity is the velocity of the current and the velocity of the swimmer. Since it is in one direction, consider this as the positive direction. So this will be positive 10 meters per second plus positive 25 meters per second. And the velocity of that the observer sees, or the resultant velocity, will be positive 35 meters per second. Or you can say that the observer on this case, on case A, sees that the swimmer is swimming with a velocity of 35 meters per second with the current or east or whatever is the direction. Now let's see the second situation when it is moving against. So the vector diagram in that case will be something like this. This is the velocity of the current, and then the velocity of the swimmer will be on opposite direction, which will give us the resultant velocity, this vector here. Now mathematically, again, this is graphically, and that the river situation, when you see the river is the situational diagram. This is the vector diagram. And now mathematically, what do you have is the resultant velocity is always the current plus the swimmer. You assign, those are collinear, you assign one direction as the positive direction, any direction will be okay. And then you say this is positive 10, because you assigned the going east as a positive, plus negative 25. So this will be negative 15 meters per second. And you can say that the resultant velocity, or the velocity the observer sees, is 15 meters per second against the current, or if you are assuming that the current is east, then you say the opposite of east is west. Okay, the third situation is when you are crossing the river, and we will see what is the time that the swimmer will reach the other side of the river. So what do you have in this case in terms of the vector diagram is that you have the velocity of the current is still going east, and the velocity of the swimmer is heading straight north, which will tell you that the resultant velocity, or the velocity that the observer sees, is a vector like this. Therefore, again, the resultant velocity, I'm not changing anything in terms of the what is mathematical. How do we start mathematically solving it? This is what we have. The resultant velocity is the velocity of the current plus the velocity of the swimmer. In a difference with the first two cases, this is a two-dimensional one, and we will solve it using components. So horizontal, vertical, this is an easy one, but still we'll do it. A swimmer and the velocity of the resultant. So velocity of the current will be positive 10. and 0, and the velocity of the swimmer will be 0 and positive 25. So the resultant is positive 10 and positive 25, which tells us that the magnitude of the resultant will be the square root of 10 squared plus 25 squared, and the whole thing square root. So 100 plus 25 squared is the whole thing square root is 26.93 meters per second, and the direction is the inverse tangent of 25 over 10. So inverse tangent on 25 over 10. Please make sure that the mode is on degrees. Is 68.2 degrees. Now, if you have a river that is, we said 150, I believe, then you have this as the vector diagram. We said that the resultant velocity is a combination of two independent, uniform motion. So now, and this is 68.2. Now, if you are starting at point A as a swimmer and you are heading at point B, you are actually ending up at point C, that is with an angle of 68.2 meters with the shore as a result of this current. So now, the time that will need, this being 150 meters, the time that you will need to go from A to B is the same as the time that you need to go from A to C, and is the same as the time that you are moving from B to C. So if I'm asking you what is this time from A to B, then will be the distance AB over the velocity on the direction AB. And if I'm asking what is this time, then you will go whatever is the distance A to C over the velocity on the direction A to C. And if you are using finding what is the time from B to C, then you will go the distance BC over the velocity on this direction. But the velocity on the direction AB, so direction AB is this one here, is actually the velocity of the swim. The velocity on the direction AC is the resultant velocity, magnitude of the resultant. And the direction on, or the velocity on the direction BC is the current, the velocity of the current. So those times are the same. Okay, so if we have 120 meters wide river and we are using this number, then we are using the distance AB. So therefore, we will use the velocity of the swimmer. So the time that it needs to move to reach the other side of the river will be 150 over the velocity of the swimmer, that is 25 meters per second. Or you can say that it is whatever is the distance AC over the velocity that we just calculated it as 26.9 meters per second. Or if you want to figure out what is the time that is going downstream, then you will use the distance BC over the velocity of the swimmer that is 10 meters per second. So this is the same thing. What we are doing here is the same quantity. Those are the same. From here, you can find what is AC, or you can find AC using the right angle triangle or anything that you want. And the shortest time will be this one here. Okay, if you are going on this direction here. Okay, now let's move to the fourth situation where we have a river that is again 150 meters, and now what you are doing is you are going from A but heading at a certain direction so that you end up at point B. Okay, now again we will keep the same numbers for simplicity, as the velocity of the current is 10 meters and velocity of the swimmer, and we will find the direction that the swimmer has to have in order to end up at point B, straight up. Now we will start as always that the resultant velocity is equal to the velocity of the current plus the velocity of the swimmer. And on this relationship, we know the direction of the velocity of the resultant velocity, but not the magnitude. For the current, we know both the magnitude and the direction. And for the swimmer, we know what is the magnitude, but we don't know the direction. So magnitude is yes, magnitude, and this is direction, and direction is a question mark for the swimmer. Now, if we rearrange this equation, then we will have the velocity, resultant velocity is equal to the swimmer velocity is equal to the resultant minus the velocity of the current. Since we are dealing with 2D, then what we do is we build the table of components. So horizontal, vertical, and then we have the resultant velocity, the current, and the velocity of the swimmer. So the horizontal component of the resultant, since we know will be on this direction, is 0, and the vertical is positive whatever is the resultant that we will find, and the current, the horizontal, is positive 10 and the vertical is equal to 0. For the swimmer, the velocity of the swimmer, we have, let's say, an x and a y. So now we have that the horizontal component of the swimmer is equal to 10. Oh, this is negative, so negative here, and it's negative 10 meters per second. And what do we know? That the horizontal component of the velocity of the swimmer will be, if this is the velocity of the swimmer, this will be the horizontal component of the swimmer. So if we assign this angle beta, then this negative 10, and it's negative because it is going in the west direction. So this negative 10 and negative 10 will be as a result of cosine. Okay, so negative 10 is equal to whatever is the velocity of the swimmer, times cosine of angle beta. From here, we find what is angle beta as we know the magnitude of this as 25. So inverse cosine of 10 over 25. Sorry. 66. So angle beta will be 66.4 degrees. And this is the angle with the shore or the side of the river. And now we know what is the y, because the vertical component will be this vector here, vertical component of the swimmer, and or this vector here, and will be whatever is the velocity of the swimmer times sine of angle beta that we just found. So will be 25 times sine 66.4 degrees. So, and this is equal, based on the equation, is equal to y and is equal to the resultant velocity. So 25 times sine of the angle is 22.9 meters per second. So from here we find out the direction that the swimmer has to have is at 66.4 degrees with the river, with the shore of the river, or you can go with the north, 90 minus 66.4, and the resultant velocity is 22.9. So now let's take those numbers and then see what is the time that it needed to reach the other side of the river. So this is the velocity of the swimmer, as 25, and this is the resultant as 22.9 meters per second. So now if we are finding the distance, so this is where it starts at point A, point B, and this is where we'll have if it was a still water. So it's C. Now, the distance from A to B, we said that is 150 meters. The angle here is 66.4 degrees. So we can say that the distance from A to C is, using trig ratios, is 100. So AC is 163.69 meters. Now time, as it is going from A to B, will be distance A to B over the velocity on A to B, which is 150 over the resultant velocity. So 150 divided by 22.9 is 6.55 seconds. And if you are using this, will be the same time, but this in comparison to the time that we found on the previous case is less. So the shortest time, if you have a river, and you have several options, so let's say option 1, option 2, option 3, and option 4. The one that produces the shortest time is this one here. And now the last part of kinematics is projectile motion, which is a combination of uniform and non-uniform motion. And uniform is in the horizontal direction, and non-uniform is in the vertical direction. In order to solve any projectile motion, what we do is we build again a table, because we love tables. Horizontal and vertical is uniform and non-uniform. And on the uniform, we have acceleration as equal to 0. On the non-uniform, we have acceleration as equal to the acceleration due to gravity, which near the surface of the Earth is 9.81 meters per second squared, and since it is going down to the center of the Earth, will be negative 9.81. The velocity in the horizontal is constant because we are dealing with a uniform motion, and will be whatever is the horizontal component of the initial velocity, and the velocity in the vertical will change because will be affected by the acceleration on that direction, and will be whatever is the vertical component of the initial velocity minus the acceleration times time. And then the range or the horizontal displacement will be whatever is the horizontal component of the initial times time, and the height will change when, as a projectile, will be whatever is the vertical component times t minus 1/2 times 9.81 t squared. The way that we approach projectile is we build the table based on the information that we have for the initial velocity, meaning that we find the horizontal and the vertical component of the initial velocity, and then we build this table, and then we solve based on the information that the problem is giving us. We'll stop here on the how does the graph look like. So for the horizontal velocity, what do we have is either a positive or a negative. A positive is the case when the initial velocity is something like this. And so this will be this case here. And a negative is when you are at the cliff and the velocity is in no, horizontal is always positive. Horizontal is always positive, sorry. Horizontal is always positive. Okay, then the acceleration for the horizontal will be 0, while the displacement of the horizontal will be this one here, and the slope will be the horizontal component of the initial velocity. And for the vertical component of the velocity, the graph will look something like this, where this at this point here is where the maximum is reached. Okay. It may be negative, as in this case, yes, we may have a negative one. So if this is the vertical velocity, then we may have a negative one that goes like this. And this case is when you are at the cliff and you are throwing it with an initial velocity that goes like this. Or it may be equals to 0, starting at 0. Maybe something like this, when we are at the cliff and the initial velocity is this one here. The acceleration in any point on projectile is negative 9.81. meters per second squared, while the displacement in the y is projectile or trajectory. And this is it. If you want to see more details on how to solve projectile motion, then you can refer to the videos on projectile motion.